disciplines, our other sectors and areas of discovery. So we will hear about the influence that the process of learning about the nature of the universe, the influence that it has on, for example, the medical field, environmental monitoring, food safety. There are many others that Fabiola will talk about. And then, of course, there is a fundamental aspect to the collaborative nature of the discovery that we will hear about. So before I hand over to Fabiola, let me introduce Fabiola herself. She is Director General of CERN and has been so since the beginning of 2016. She's the first woman in this role and the only person who's been re-elected to lead CERN for a second mandate of 5 years. By training, she's a subnuclear physicist. That's a PhD degree she holds from University of Milano. And in her work as a researcher, one of the things she led was this ATLAS experiment, which uses Large Hadron Collider. And while you may not be familiar with the ATLAS experiment itself, you are almost certainly familiar with probably its most famous discovery, and that's the Higgs boson, the so-called God particle. You probably remember that term. That's how it was reported back in the day. And believe it or not, that was just over 10 years ago. And in fact, last summer, there was a wonderful celebration, 10 years. So of course, the announcement was made and indeed led by Fabiola back in 2012. Last year in the summer, there was a 10th anniversary celebration. In fact, at Nature, we celebrated it by publishing follow-up research and also celebrating the history itself. Fabiola holds a number of distinctions, awards, and honorary degrees. I will just mention 2 points because I think they're really worthy of mentioning. She's been included among top 100 most inspirational women by The Guardian newspaper and top 100 most influential women by Forbes also. So here we have an inspirational woman and an accomplished physicist to tell us about the mysteries of the universe, the insights into it, and how those influence other fields as well. Fabiola.
Thank you very much, Magdalena. Thanks. Thanks a lot. Thanks, Magdalena, for this very nice introduction. And also thank you for the opportunity to describe the science we do at CERN. So what is CERN? CERN is the largest laboratory in the world for particle physics. And particle physics is the most fundamental of all sciences because it studies the smallest constituents of matter and of the universe. Constituents that cannot be cut into smaller pieces, and therefore they are called elementary particles. CERN is based in Switzerland, in Geneva, close to the border with France. And here you can see an aerial view of the region with the lake here, and Switzerland on the bottom part of the screen, and France on the top part. And the ring, the circle you see, indicates the location of the Large Hadron Collider. It's the most powerful accelerator humanity has ever built. It's a 27-kilometer ring, 100 meters underground, where we accelerate 2 beams of protons in the 2 opposite directions of the ring, and then we bring them into collisions at 4 points. But what is an elementary particle and what is its size? So let's start from something that we know, a human hair. Okay, this is a human hair. So the size is 100 microns, so 1/10 of a millimeter. A micron is 1 millionth of a meter. And then if you go down deeper into the structure of metals, we find cells, of course. And then going deeper and deeper, we find various structures, fibrils and proteins, for instance. Here we go, keratin. And then if we go down and deeper, we found atoms. In the case of air, we have nitrogen, sulfur, oxygen, and carbon. Now, atoms are not elementary particles. They are made of substructure. They are made of a central nucleus surrounded by a cloud of electrons. Electrons are elementary particles, whereas the nucleus is not. it's made of substructures. And these substructures are called neutrons and protons. They have a size of 1 Fermi. A Fermi is 10 to the minus 15 meter. Neutrons and protons are not elementary particles. They are made of substructures, and these substructures are called the quarks. The quarks are elementary particles as far as we know today. So electrons and quarks are the fundamental constituent of matter. They are elementary particles, and the matter, all the matter we are made of, all us human beings, is made of electrons and quarks. When I say all human beings, I mean everyone. So even the VIP here in Davos, even the head of states, everyone is made of electrons and quarks. So science and CERN exploration with the Large Hadron Collider allows us to study matters at the level of its fundamental constituent, the quarks. So on physical scales of 10 to the minus 18 meters or smaller, so a billions of a meter. So in some sense, accelerators can be compared to big microscopes. The smaller the structure you want to study, the more the energy you need, because you need a very high resolution power. So if to study human cells, you can just use a microscope in a lab. If you want really to study matter at the most fundamental level, you need to use big accelerator with a lot of energy, and we will see how this is done. At the same time, this study of the very, very, very small allows us to study the very, very, very big, so the structure and evolution of the universe. Today we know with high precision that the universe has been at the origin from a big explosion some 13.8 billion years ago. At the beginning it was very hot and very dense, and it was essentially gas of elementary particles. Then it expanded and cooled down, and then the elementary particles started to get together. First the quarks to form neutrons and protons, then neutrons and protons to form nuclei, nuclei with electrons to form atoms, atoms to form molecules, and then up to the macrostructure that we see here, stars, planets, galaxies, and of course us, the human beings, and our hair. So this is the reverse movie of what I showed before. So the Large Hadron Collider allow us to probe the universe at times corresponding to 10 to the minus 12 seconds after the Big Bang, 1/1,000,000 of a second. So what does this mean? It means that the energy that we produce in the collisions of the two proton beams corresponds to the temperature that the universe had at this time. And the temperature was 100,000 billion times the temperature in this room. So we are able, so these numbers are quite impressive, we are able to reproduce in the lab, in controlled condition, we are able to reproduce the phenomena that characterize the very primordial, the very early universe. So the elementary particles that were there, the interactions, the various phenomena that took place. To do that, we need three big classes of instruments. We need particle accelerators, we need particle detectors, and we need powerful computers. So let's start from the accelerators, and here we are back again to, quick again, yes, to the ring. So as I said at the beginning, we inject two protons in the two proton beams in the two opposite directions, and we accelerate them at the largest possible energies. The limit only comes from the technology. The technology is superconducting magnets that are needed to provide a very strong field to keep the beams on the circular trajectory. And these two beams collide in 4 experiments. So these are 4 giant instruments, underground instruments. When I say giant, I mean a cathedral. Take, half Notre Dame and put it underground, okay? And the goal and the purpose of these experiments is to detect the product of the collisions. So you have these high energy beams colliding. The movie should go on. Yes. Colliding in these big underground instruments, and they produce thousands of particles, and the task of the detector is to measure every single particle produced in the collision, identify those particles, measure their energy, reconstruct their trajectories, and give us a picture, an image of the collision event. So if accelerators can be compared to giant microscope, particle detectors can be compared to digital cameras that take pictures of the collisions. But you know, it's very special in high-tech cameras because the two particle beams collide 40 million times a second. So this detector must be fast enough to look and to take picture of the events and then discard those that are not useful or interesting, and then save to storage only those that can be that deserve further study. So from this you can, for instance, deduce if you have produced a Higgs boson, a W, a Z particle, and then study you know, the constituent of matters with very high precision. All this will not be possible without the contribution of scientists from all over the world. So CERN attracts some 16,000 people, technicians, scientists, engineers, physicists from all over the world. More than 110 nationalities are represented. We also have scientists coming from underprivileged countries, so in this case our mission is capacity building, and some of the scientists actually come from countries that are not the best friends of each other, actually countries that are in conflict, and they work together at CERN animated by the same passion for knowledge. Computing is also extremely impressive because we have a distributed population across the world, so we need distributed computing. So at the time of the conception of the LHC, CERN and its partner developed what is called the LHC computing grid. So a grid of more than 150 computing centers distributed across the world and connected by very fast links and networks, providing a storage capacity of 2 exabytes and something like 1 million processing cores. Now, this instrument, detectors, accelerators, and computers are extremely sophisticated. For instance, in the case of computing, the LHC computing grid has paved the way to the cloud. So really instruments that develop and that are based on very on cutting-edge technologies that in some cases are really pioneering technologies. These technologies are transferred to society to the benefit of everyday life. And they are transferred free of charge, because the founding convention of CERN, which was signed by the member states back in 1954, states that everything we do, the results of our research, the technologies we develop, are available to everybody free of charge. This is what we call today open science, but already there, 70 years ago, that was already present in the founding convention of CERN. So I will give you some example. Everybody knows that the World Wide Web was invented at CERN by Tim Berners-Lee. At the time he was working as a CERN employee. But other examples are, for instance, accelerators that are used to treat cancer using proton, ion, and electron beams, which for some tumors are more effective than the conventional radiotherapy, and also in particular because they do not have side effects. They do not create problems to the healthy tissues. Superconducting materials have the possibility of wide application. The image was too fast. I cannot go back in a moment. But the previous image showed a radiation dosimeter on board the International Space Station. And here you can see here is a high-resolution 3D color image of a medical image made with CERN electronics. So several decades of exploration at CERN and in other laboratories for particle physics across the world allowed us to discover several elementary particles, they are shown here, and understand their properties in detail and their interactions. The last one to be found is the Higgs boson, which was discovered at CERN 10 years ago, as Magdalena correctly said, a very special particles without which atoms, of which we are all made, will not exist as stable systems, so we will simply not be here. However, these particles and this interaction only explain the so-called visible universe, which is 5% of what is out there. The rest, 95%, is made of former matter that we don't know, and we call them actually dark matter and dark energy. Dark indicates, on one hand, our ignorance, and on the other hand, the fact that they do not interact with our instruments, so we don't see them. And I would like to conclude with a beautiful image of the sky. Whilst what really strikes us in this image is, of course, are the stars, the galaxies, the bright objects, actually the most fascinating, the most intriguing part is the dark. The dark is today mysterious. We don't understand the dark universe, and that's a focus of scientific exploration today and tomorrow. Thank you.
Thank you. Thank you very much. That was terrific. And a couple of reflections, if I may, and then I start off with a question. I hope you have began to formulate questions of your own. Really striking couple of reflections as you were speaking. The first one is that fundamental unity of us all. And of course, it's not just the VPs and the politicians at Davos. It's all matter around us. So that fundamental uniting basis to not just life, but everything that exists on this planet and, of course, in the universe. And the second thing, just now what you said here about the fundamental discoveries, the fundamental research such as this teach us how to look at problems and what it is that may be interesting. Exactly as Fabiola said, at first glance, it seems all the shiny things are really interesting. And of course, they are interesting.
But more important is...
Exactly. More important is what's in between, in part, because that's the most mysterious aspect. And so let me start with the first question, and please get yourselves ready. So I rather suspect that the image you're showing here is from the James Webb Telescope, right? Yes. We've, of course, seen so many images already over the last few months, last month of the year. You illustrated very beautifully how recreating these very early moments in the history of the universe sheds light on that history. How does it compare, the information that we're getting from a really powerful telescope like James Webb and the information that we get from experiments at CERN?
So thanks for a very good question. So I showed a very complex image showing a picture of the evolution of the universe, and showing on the two ends the telescopes and the accelerator. So the two types of instruments are complementary. Telescopes try to look at the structure and evolution of the universe by looking at the macro objects, stars, galaxies, etc. And by looking at the farthest object, they allow us to go back in time. Accelerators are able to go back to more primordial epochs, at times where light was trapped by the very dense early universe and could not escape, so could never come to us. And so so accelerator can go farther back in time, and of course the information that comes from both can be combined and can give us a more complete understanding. Of course, as I said, there is still a lot to be understood. Dark universe, dark matter, dark energy. There are different interpretations, for instance, for the nature of dark matter. And so by combining also the information from telescope and particle accelerator, another experimental endeavor like big detector underground that look, for instance, the dark matter coming from the intergalactic halo and interacting with the detector itself, we can try to get the full picture and the right picture.
Thank you. Any questions from the audience or comments? Please go ahead. There's a microphone coming to you.
Hello. I believe 10 years ago, after you discovered the first Higgs boson particle, what is the next aim or goal of CERN?
Thanks. Thanks very much. Well, it's to, the goal of CERN is to address, as the goal of all scientific endeavors, is to address the outstanding question. So the discovery of the Higgs boson allowed us to answer one of those questions, the origin of the masses of the elementary particles, which is absolutely essential to understand why atoms are stable systems and why we are here. The Higgs boson itself, it's a very special and very peculiar particle. It's part of this standard model of particle physics. I showed one slide without going into the details, but if you look at the details of the theory, all the problems in the standard model, which describes very well the elementary particles and their interaction, originates in terms related to the Higgs boson. We don't understand its mass, we don't understand fully the way it couples, we don't understand the vacuum that is related also to the Higgs boson. So there are many, many questions that are related to it. Beside the Higgs boson itself, of course, what I said, dark matter, for instance. If dark matter happens to be made of particles that have masses at the level of from a few hundred GeV to a few TeV, it can be produced in proton-proton collision at CERN. If it's made of something something different, like primordial black holes, then other instruments are more suitable to are suitable to detect it. So we will continue to address these open questions, and I can't tell you which one will be answered first. This is in the hands of nature, but of course it's very fascinating that we have those interesting questions, but also that we have learned with time what are the right questions to ask.
You are next, I think. If you just wait a second for the microphone.
Thank you. Doctor, it's so fascinating, and it seems to me that there is such a big advancement, but there is a disconnection sometimes between all this advancement and what kids are learning in school. And they still are being taught the very basics of the atoms and the electrons and the protons, and not so much of what really is happening, what the scientists like you have discovered. So the question is, how could we help the scientists to actually take all these learnings and teachings to the younger kids and the younger generation that will come after you, and hopefully advance beyond what you have achieved?
Thank you. It's a very good question. It's true. Now, if you look at the textbooks at school, in some cases you find the Standard Model, and maybe in some cases you find the Higgs boson, but in most of them you don't. You find mainly classical mechanics, very little quantum mechanics, not even in very simple, in the simplest term. I think it's very important that we scientists continue to communicate and to educate the younger generation. I would like to mention maybe a project that we are realizing at CERN. It's called the Science Gateway. We are building a new building complex where we will have, of course, exhibition and many interactive activities for the general public, but we will also have labs for kids starting at the age of 5 all the way up to 16 until they go to a university or so, where the kids can come and do experiments with their own hands and understand what being a scientist means. And this means having a question and a problem to solve, building the instruments, making the measures, and share the results with their peers, so the other kids at school, in their case, with other scientists in our case. So I think if we all scientists in all our labs or research infrastructure try really to attract the public, we also have at CERN, like in many other laboratories, programs for the high school teachers that come and spend some time with us. This is also an important message because they get an update on modern physics, and they can then make pressures so that the textbooks and their teaching at school is up to date.
There was a question in the middle and then at the front.
Thank you for the presentation. Do you use artificial intelligence in a meaningful way in your research, or if not, are you planning to do that?
We do, and actually CERN is really very much on the front line for developing of machine learning and AI techniques, of course, because the problems that we have to solve are extremely complex. When you look at this, these collisions of proton beams, you produce thousands of particles, and so sometimes the signal that come in the presence of particles that are produced very rarely, like the Higgs boson. The Higgs boson is not produced so often. You need to extract very tiny signal from a large number of data. So very complex analysis techniques and very complex algorithms. And there is exactly where AI can help. So really, we are really using this, and because our requirements are extremely stringent, this is also, CERN is also very often a test bed for companies developing AI or developing technologies on quantum now that can be used for more advanced algorithms. And so, yes.
There's a question here in the front row. Can we go the front first, please? Just here on your right.
Michael Jan from Denmark.
Hi.
First of all, it's fascinating what you're telling, and I'm still struggling by understanding that the most important is the darkness here.
Exactly.
So my question is, when we come back in 10 years' time, do you expect that we will see more dots on this photo? And then another question on the more political thing is, you talked about open science, which is also fascinating, but how is that affected by the global geopolitical war between China and USA, for example? Is it threatened, this open science?
So starting with the first question, which is easier. No, I'm joking. I can't tell you if in 10 years from now we can, you know, put a name on the particles or the forces or whatever that, can explain the dark universe. This I can't tell you. I hope so, at least for part of it, dark matter, which is maybe a little bit easier, in quotes, to solve. It depends on really what nature has put out there. Of course, but I can tell you that dark matter and dark energy are the objective of an extremely broad class of scientific endeavors, not only accelerator physics, but also telescope and other studies. Now, of course, gravitational waves detection and study comes in, so what we call multi-messenger astronomy. So we are doing huge progress in the technologies and in our way of exploring the universe with very complementary instruments. So I think that we can get nice results, I hope, soon, but I can't tell you when. Concerning open science, for the time being, you know, the game of the rule at CERN is that what we do is open science, and we have collaborators from the US, we have collaborators from China, and this has never been questioned. It's a value of CERN, it's a mission of CERN.
If I may follow up on this, I think you opened up with the second part of your question, a really, really interesting issue here about open science, but also collaboration more broadly. So this openness, information exchange, I always think much of this research, and indeed what you talked about in the context of CERN, happens in an academic context. But of course, there's research that happens in the private sector and relevant to this, but also other disciplines. And there is, I think, a real opportunity to consider how in an open, collaborative way there may be exchange of data and information in this sort of pre-competitive space, if you like.
So, right, good point, Magdalena. So first of all, it's true that it's much easier to be open in an academic world. In our case, for instance, we do not develop many technologies that have a potential dual use. So, you know, it's so security issues are not so important, and also limiting or constraining in our case. So it's much easier in the purely academic world than in the private sector or at the level of government or activities that have a direct link with government, security, etc. However, it's also true that there are other fields where global sharing of data is not a practice. It's not, you know, in some medical fields, for instance. This came up at the time of vaccine, for instance. So I think it's important that we try to push for open science, for data sharing and sharing of information, because open science has many virtues. First, it boosts science itself, because the more you exchange with other scientists, the faster science goes. Second, it maximizes the impact of science on society. And third, also, is a very powerful means of reducing the inequities across the world, because, of course, if everybody has access to science, education, and technology, of course, for free of charge, then, of course, you reduce the gap, which today, unfortunately, is widening with the technology, having such a disruptive evolution, disruptive in a positive sense, and being extremely, you know, growing very fast, the gap widens.
Exactly, and the impact on society, you can also extend it into thinking in terms of trust in science, right? And that, of course, is something that
absolutely
the science community, research community, is very concerned with. You mentioned vaccines. We saw that.
Exactly, which can, of course, can help to fix this real or perceived mistrust in science through, again, open science and sharing technologies and showing the impact of science, but also through communication, transparent communication. This is what I was mentioning before.
Exactly. Other questions? I think there was a question there. There's a question here now.
Thank you very much. I'm the Italian ambassador to the United Nations in Geneva, including to CERN, Gianlorenzo Cornado. I want to congratulate you for hosting this event and congratulate the Director General Fabiola Gianotti for her presentation. She's quite unique because she can explain very complicated issues to people who are not specialists. And I believe there are very few people like Professor Gianotti capable to do that. I have a lot of admiration for her. I have a question on the universe. Thanks to the accelerator, we are capable to study the origin of the universe. You believe it will also be possible to predict the future evolution of the universe and to understand whether the universe, after having had an origin, will also have an end? Thank you.
So what we know, I can answer by maybe elaborating a little bit on this concept of dark energy. Actually, we have here in the room Brian Schmidt, a Nobel laureate, who is the person who has understood within the group of Berkeley also that the universe is expanding today at an accelerated pace. So you can imagine the initial explosion of the universe, the Big Bang, and then the universe expand and then cools down. I can imagine that at some point, because of the gravity, so the various masses form, because of the gravity, then the various masses tend to implode, and the universe at some point will implode, and we'll go back to, say, the very initial state. But we have discovered that some things about 5 billion years ago or so, the universe started to expand again at an accelerated pace. And this we don't understand. We think that there is a form of energy, a pressure, so it's a scalar energy, scalar force, a pressure that pushes the universe apart, every single point away from each other, and counterbalance the gravitational attraction. So we are accelerating now we are in accelerating expansion phase. This is what we can tell today.
We have run out of time for any further questions. I'm actually delighted to see how many questions there have been. Fabiola, that's credit to your ability to tell the story in this very, very engaging way. A couple of final comments. I really want to emphasize for you that incredible fascination and hunger for understanding of the very fundamental properties of matter and the universe around us, and how that fundamental interest in getting to the bottom of everything that is around us and within us unites us all. Yes. And you talked about collaboration among scientists from parts of the world who don't come together, don't convene, don't have a seat at the same table in really any other situation. And that's one power of science, which I think we don't talk about
it's a glue.
Enough. Absolutely, it's a glue. Thank you very much.
Thank you, Magdalena.
Fabiola, and thank you to all of you.